Okay, in this video, I want to go through, again, a review of simple linear regression, move on and include the Anova table, and then a couple more things. So in this sheet, I just have some values of x, for x 3, 6, 4, and so on, for y 4, 6, 2, and so on. And I've computed the means and the deviations and the squared deviations as we have before, and also the cross products. Then got the average, the standard deviations, and the covariance. You can kind of look through there and just take a couple of minutes to review these calculations. We've done them before. I'm going to move on, so if you need to, hit pause. And there's a 6 under there, over on the right towards the bottom. Yeah, I'm not sure what that's for. Just ignore it, please. And there aren't any new calculations on this page. Just wanted to indicate to you that the 58 there is the sum of squares total. It's the same thing we've used in the numerator for the calculation of standard deviation and variance throughout the class. Okay, so now I want you to focus here. This is just some points. These aren't in line with the day that we have here. This is from an applet that I'll give you the link to in a minute. What I have here is just the mean, 60. Again, this doesn't fit with our data. It's just a geometric depiction. So that mean is 60, and then there's points around that line. So throughout the semester, we have been calculating deviations from the mean. That would just be y sub I minus y bar, each one of those lines. Then we squared those. So we just took each of the deviations and squared them. And then when we add all of those squares up, the area for all those squares, we'll get the sum of squares total. And the problem we're working now, that's 58. You've seen a couple of times already. But this is what it would look like geometrically. You have the mean, in this case a little more than 60. Deviations from the mean, that's the y sub I minus y bar. The squares, those are the y sub I minus y bar squared. And then the sum of the squares, or sum of squares total, that's the area of the whole squares, or the sum of the y sub I minus x bar. I'm sorry. The sum of the y sub I minus y bars squared. And then like I said, add those up. Again, I'm just pointing that out to you. In this problem, 58 is the sum of squares total. It's the sum of the squares around the mean of the data, around y bar in this case. Okay, now I've just added one calculation. I had the R of 0.876. That was the sum of the cross products, the 34, divided by n minus 1. Now I'm thinking that 6 might have just been a count for the sample size. So anyway, I squared that R to get R squared. That's just like eta squared when we did the analysis of variance. That's the proportion of the variation around the mean that's explained by the regression line. So that variation around the mean was sum of squares total that we just calculated, the 58. So now I've computed A, the y-intercept. There's a formula for it. And then B, the slope for the line. Actually, if you're using these particular formulas, you need to compute B first, because B is a formula in the y-intercept formula. There are other formulas out there, especially for the slope. Once we have this intercept and the slope, we can write an equation for the line that would best fit those blue points we had on the previous slides. So y hat, that's predicted value of y, is equal to A, the y-intercept, plus B, which is the slope, times whatever value of x for which you want to predict y. You can be a little less concerned with the calculation of A and B. Probably use calculators for that most of the time, but I do want you to go from there to the line and kind of understand what's going on. Alright, now we're going to just go a little bit deeper into this. The shaded column here is the original x's. 3, 6, 4, and so on. The y hat, I'm taking each one of those x's, plugging it into the regression equation, the minus 0.4 plus 1.38 times x, to getting what we would predict for y at each value of x that we have here. So if x were 3, our regression line would predict a y of 3.385. If x were 6, plug that into the equation, and we would predict y to be 7.308. Be careful on these predictions, especially if you move beyond the data, that you stay within the values of x. We've talked about the domain of x a little earlier in the course. Anyway, now I put those x's away, keep the y hats, and write down the y's. These are just the original y's that we had in the problem, the 4, 6, 2, 12, 5, and 7. Let me recap here. The y hats are, we put the x's into the regression line, and this is what we have. The y's are just the original y's. Okay, so now that we have y and y hat, we're going to do y minus y hat. So 4 minus 3.385, 6 minus 7.308. See, I've got a little bit of rounding in there. Actually, I probably just didn't, when I did this on a spreadsheet, didn't carry out both columns to the same number of places. But you can see here that that could be minus 1.308 when you did 6 minus that. So now we have, when we have these y minus y hats, what we have is deviations from the regression line. So now instead of talking about deviations from the mean, when we had y sub I minus y bar, we're going to talk about deviations from the regression line. And of course we're going to square those and add them up. Seems natural, doesn't it? And so, well, maybe it doesn't. When we sum and square those, that's going to be SSE, the sum of squares for error. Okay, just recap here. That is the sum of squares around the mean. We did that earlier. Should say, for the problem I've been working there, it's SST equal 58. Make that correction, please. That should be at the bottom. For the problem I've been working, SST is equal to 58. Residuals are the distance of every point from the line. So when we're talking about difference from the mean, we call it deviations. Residuals, it's exactly like a deviation, except for it's the distance from the regression line instead of the distance from the mean. Naturally, if we have deviations, residuals, we're going to square those and add them up. That's where we had the 1354 on this, well, about 2 or 3 slides before this. Again, the numbers that I'm reporting here are numbers for the problem I'm working. They don't really fit the numbers that are on here, but I just want you to get the geometry of it here. Okay, so this is just going to recap everything. We have the mean, and we have the points. We can show the deviations here from the mean. We can square those, and we can add them up. For this particular set of data, that would be the numerator for calculating variance or standard deviation. I'm going to hide all those again, and I'm going to put the least squares line there, and I'm going to get those differences, and I'm going to show those squares, and these ought to be smaller. If you have a good regression line, as we do here, the points are pretty close to it, they ought to be a lot smaller. In fact, if you took these areas and subtracted them from the original areas that we had around the mean, we would have sum of squares regression, sort of like sum of squares treatment when we were doing analysis of variance. Again, the sum of squares is for the error, or SSE, for this particular problem here. Now I'll just move on here. This is just another kind of look at what we've just done. Now, what we have here is individual values of y and y bar. You know this isn't exactly right because if y bar can't be below all of the points, there's going to be a lot more on this particular page. But if this were exactly correct, there would be a bunch more points below the line as well. But anyway, this bracket is the error or the deviation with respect to the mean. So y sub I minus y bar. Now, when we bring in the regression line and predict here, see, originally we were basically, for every value that we have, every y sub I, we would still be predicting the mean if we had no other information and we just want to know what the next value is, we would predict it to be the mean. But now with this regression line, our prediction gets a lot closer. So that brown line, the brown bracket there, is how much error we've eliminated. So that's going to be SSR. The area that I don't have in the brackets from the when I go from the line that I have here between the blue and the brown dot, that would be the error term. Of course, you'd have to get that deviation, square it, and sum it to get the whole SST. But you might want to look at this model and pause if you need to, just to kind of see how these relationships fit. Again, this is just for one point. We haven't done the squaring and summing yet. But if we take that error that we've eliminated by y-hat model or by the regression line and divide it by the area around the mean, the sum of squares around the mean, we will get the proportion of error eliminated by the y-hat model. And by the way, that proportion of error eliminated by the y-hat model is called r squared. This numerator is basically SSR, and then SST is the total error around the mean. And that ratio, SSR to SST, is r squared. It's the proportion of variability accounted for by the given model, or by the regression line would be another way to say that. Okay, so let's put a couple of things together here. SSR is the sum of squares attributed to the regression line, just like or at least analogous to SSTR when we did the one-way Anova. SST is equal to SSR plus SSE. Again, you can maybe think about this is an analog to the Anova model too. The total variation around the mean is broken up into two parts. The amount that we can assign or attribute to the regression line, and then the remaining error, which is just residuals around the regression line. Since those add together, SSR is equal to SST minus SSE. We had SST as 58, computed that a minute ago, computed SSE to be 1354. The difference is 44.46. That's sum of squares regression. Earlier, when we computed R, just like we did a few weeks ago, the covariance divided by the product of Sx and Sy, we got R of 0.876. It's back on like maybe the second or third, actually on more than some slides there at the beginning. Well, if we square R, we get 0.767. And if we take SSR divided by SST, we get 0.767. So R squared is the proportion of the total variation, or the total sum of squares, that we can attribute to the regression line, the SSR. Okay, the next page presents the Anova table as it relates to regression. You need to study that carefully, and what you'll see is that it's very similar, at least analogous to the Anova table when we did the one-way Anova. You can see that it has the sources, the source regression, set of treatment, error, and then total. So we've already calculated the total and the error to be 58 and 13.54. Then we got the difference of those to be 44.46. The degrees of freedom for the regression is the number of predictors. In this case, we only have one X, and that's all we'll have in this class. So for this class, that degrees of freedom for the regression will always be 1. If you were to go on and take additional courses, you'll do something called multiple regression. Probably be one of the first 2 or 3 things you would do in that class. But at any rate, then you would just have more than one X that you're using to predict Y. Like if you're predicting sales, you would have advertising, number of salespeople, how much money you spend on marketing research, or any number of other things that you might have there. Then, if you had 3 of those things that we're using to predict, the degrees of freedom would be 3. Number of predictors, in our case, always 1. The degrees of freedom for the error term is sample size minus 2. So our sample size was 6. Subtract 2 and you have 4 for the degrees of freedom. Total degrees of freedom is n minus 1, as it has been all course. So 6 minus 1 is 5. Of course, if you took that 58 divided by 5, you would have the sample variance. Took the square root of 58 divided by 5, you would have the same sample standard deviation we've been computing all semester. We're going to get the mean squares, so just take each sum of square and divide it by its corresponding degree of freedom, or degrees of freedom, just like we did in one-way Anova. So 44.46 divided by 1, 13.54 divided by 4 is 3.385. Then the F-test is going to be MSR, that's the 44.56, divided by MSE, the 3.385, that's 13.13. We'll have to compare that to a critical value of F from a table. Then R squared, which is the analog to eta squared, is the sum of squares for the regression, that's the 44.86, divided by the sum of squares total, the 58. That comes out to be about 0.77. Okay, so using the F-test to test hypotheses concerning the regression equation, HR will be there is a linear relationship between X and Y. HO, there is not a linear relationship between X and Y. Using a 0.05 level of significance, the degrees of freedom for the F-test, remember we had 1 and 4 for the regression and the error. We'll reject HO then if F-test is greater than 7.77. So we had 13.13, that is greater than 7.77, so we reject HO. There's a linear relationship between X and Y. Okay, now let's do a t-test just like we've done in some of the other videos. There is a linear relationship between X and Y. I mean by just like other videos, some of those that I've produced and put either on Blackboard or on my website. So there either is or is not a relationship. Put rho not equal to 0, or beta, the population slope, not equal to 0. Where it's not a linear relationship, we could put rho equal to 0 or beta equal to 0. Anyway, with a 0.05 level of significance, the degrees of freedom are n minus 2, that's 4. We'll reject HO if the t-test is greater than 2.76 or less than minus 2.776. So if you go to the t-table, look at alpha 05 for a two-tailed test, 4 degrees of freedom, should be able to locate that 2.776. The t-test then is the statistic, R, minus the hypothesized correlation. R is 0.876 minus 0, that's where I've got the 0.876 at, divided by the square root of 1 minus R squared, divided by n minus 2. R squared we had computed to be 0.767 earlier. Of course, you could just take the 0.876 and square it. Comes out to be 3.63, which is greater than 2.776. So you should reject HO and conclude that there is a linear relationship between X and Y. When there's only one predictor, there's some pretty nice direct and exact relationships between the F-test and the t-test. So remember we said reject HO if t-test was greater than 2.76 or less than minus 2.776. We computed that t-test then to be 3.63. Of course, then we rejected HO. On the F-test, we had said reject HO if F-test is greater than 7.7. And then when we computed the F-test, we got that to be 13.13. Except for rounding, if you took that 2.776 and squared it, you'd get 7.7. So the t-test squared is F-test. Same thing if you took the t-test that we calculated, 3.63, and squared that, you'd get 13.13. I think when I actually calculated that out, I might have gotten 13.16 or something. That was just rounding. Of